we're on to skill 3. Hopefully, after the 4 slides on the Desmos investigation, we now know that E is approximately, that always bothers me that it's not an approximation symbol. So go ahead if you have the printed out notes and fix that to an approximation. That E is approximately 2.71828 ... It is an irrational number, just like pi. And so remember, irrational numbers cannot be written in fraction form, and they are non-repeating, never-ending decimals. Ta-da! Those are your irrational numbers. Now, from the investigation, we also saw the formula for compounding interest. Before we get to that, I want to, well, let me see where it is on your notes. Yeah, let's go ahead and do that first. I want to look at your calculator. So if you need to, pause the notes, get out your calculator. If you need to borrow one of my scientific ones from the wall, go ahead and grab one. But I want you guys to locate E. Now, if you have a scientific calculator, pardon me, it's most likely on the left-hand side, not a second function. But for many of us, it is a second function, especially on the graphing calculators. It's the second function above the button that says LN. Okay, above it, you're going to have e to the x. That's your second function. So if we put in e to the x, so we hit second, I'll write that down, and then you hit e, well, natural log, right? And then you put in 1 for the exponent, you should get approximately 2.71828 ... Okay, and so E is what we derived or what we found using that formula for compounding interest when we were changing the value of some of the variables. What are those variables? Well, the first one, which is A, represents our final amount. Okay, so A represents the final amount. P represents the initial amount. What did we start with? How much money did we start with for the given problem? What did we invest? R represents the rate. And rate is always given to us in a percentage. So our account accrued interest of a 1.5% APR, right? Annual percentage rate. Or it was 75%. Pfft, yeah, we wish, right? So we need to make sure that we use the decimal form in the equation. Okay, we're going to have to convert from percentage to decimal. N, let's do purple, is the amount of times the interest is compounded annually. So it's the amount of times that the interest is compounded annually. How often it's added to the account. Running out of space. And last but not least, T represents, yep, you most likely guessed it, the time. How long did we have this account for? Well, there's a couple of things I'd like to point out. And that is that this is for, yes, compounding interest. However, a formula for the amount of money you have in the bank, if the principal amount is compounded continuously, is the equation following. A equals P times E to the RT. E, friendly reminder, is our irrational number. It's not another variable. Okay, it does have a numerical value associated with it. So big difference. If we see the words compounded continuously, we know that we're going to use our PERT equation. A equals P times E raised to the product RT power. And this is when the interest is compounded continuously on the principal. Now, usually, if it's compounded yearly, right, that simple interest formula up there, well, I shouldn't say simple, sorry. For the compounding interest formula, the first one that we see, that is compounding off of not necessarily the principal, but how much money you have in the account at each time that it is compounded. Okay, something to note, this is annually. So if I say, or if the problem says that it's compounded monthly, how many months are in a year? 12. So n would be 12. If it's compounded quarterly, there's 4 quarters in a year. So the n would be 4. If it's daily, which is weird, it would be 365. All right, so really be familiar with the different possibilities. Let's take a look at example number 4. It's asking us to find the compound interest on a principal of $10,000 at 8% interest. All right, stop right there. Couple things we know. We know that our principal amount, our initial amount, is $10,000. We know that the rate is 8%, which we're going to convert to 0.08 for the decimal. The first part, 4a, is asking us to find the compound interest if it's compounded continuously for 1 year. Okay, so we know that since it says compounded continuously, that we're going to use a is equal to p times e raised to the RT power. We know that the interest was, we know that the initial amount was $10,000. We then multiply it times e, raised to the rate is 0.08, and this is for 1 year. So go ahead and put this into your calculator with me. Please be careful. We're going to put 10,000 times, most likely you're going to hit second and then your LN button, depending on where E is. And if you need to troubleshoot with each other, please do so. And then I'm going to put 0.08 in the exponential spot, giving me my final amount of approximately $10,832.87. But be careful. What are we looking for, everyone? We are looking for the interest. So if we initially invested $10,000 and we now have $10,832.87, the interest that we earned is the excess. So the interest is $832.87. Be careful with what it's asking for, yeah? Pay very close attention. Okay, for B, same thing. It wants us to figure out the interest when we are compounded continuously for 10 years. Okay, compounded continuously says we're going to use the PERT equation. Some people like to call it PERT. And our initial investment has not changed. We're still investing $10,000. We're going to multiply it times E. The rate has not changed, but the amount of time has changed. So when we put this into our calculator, we're going to put in 10,000 times E, wherever that may be in your calculator. I highly recommend putting the exponent into parentheses to let your calculator know that the whole exponential term is being raised to that product. You could also just move the decimal place before you put the exponent in, because you know it's being multiplied by 10. Couple of options for you. All right, so our final amount is $22,255.41, rounding appropriately for money and mathematically. But we're being asked for the interest. So let's subtract our initial investment, giving us $12,000, $12,255.41 for our compound interest. 10 years, that's the way to go. All right, so that's with our compounding interest. Well, shoot, we need to be able to graph this because we know that E is a number. It's not just a variable we're going to assign to a term. Note, however, that we don't have our full Cartesian catalog for this. That's okay. we should still be able to find all the different characteristics, domain range, etc. Oh, pardon me. The thing that's a little bit different is that E is 2.71828. If I were to ask you to graph E to the negative first power, that means it's 1 over E, which is 1 over 2.71 blah, blah, blah. Holy smokes. To memorize all of these different decimals just gets really crazy. Should we be able to identify what E to the negative first is and then use our calculator? Yes, but I need you to be able to graph this without the use of a calculator. So we're going to keep it simple. Our X inputs for the parent function are going to be 0 and 1. We know that anything to the 0 power is 1. And we know that E to the first is approximately 2.71. Those are the only 2 points that I'm going to expect you to use for an exponential function with a base of E. Could you use more? Certainly. Am I going to expect you to and hope that you do? No. But can you? Yes. So hopefully that makes sense. Like with every exponential function, this does have a horizontal asymptote at y equals 0. Same reasonings as we discussed in the Skill 1 note. So if you need to, go back and look at that. Don't forget, I'm going to be having open doors on Thursday at lunch just for Trig kids. So if you have any questions, gosh, please come in. And then on Friday, we'll take a whole bunch of questions in class as needed, okay? So when we graph this, I have a horizontal asymptote at y equals 0. And let's go ahead and plot these 2 points together. We have one at 0, 1, and then one at 2.71. Now, since our base, is greater than 1, this represents exponential growth, which means we're going to increase from left to right as we draw our function, not crossing the horizontal asymptote, arrows on both ends. And that's it. That is our exponential function with a base of E. Are we going to have to transform it? Of course we are. So take a look, please, over at the second example. Notice that we do have an A value. Our A value is -2, which is just -1 times 2. So that means that we have a vertical reflection. And because the 2 is greater than 1, we have a vertical stretch. Okay, just because the base is an irrational number doesn't mean that the transformations change. Everything's still the same. H is going to be -1, taking that opposite sign, so we're going to go 1 unit left. And then K is a +3, moving us 3 units up. Okay, so we still have our transformation table. We didn't have a B value to factor away from the X, so the X column is simply X minus 1. We're going to take -2 and multiply it times Y and then add 3. So our parent function points of 0, 1, and 1, 2.71 are going to be inputted into this table so we can transform it a little bit. All right, plug in 0 with me, please. 0 minus 1 gives us -1. 1 minus 1 gives us 0. If we plug in 1 to our Y columns, we get -2 plus 3, giving us 1. Oh man, a decimal. Don't worry. We're going to go old school, everyone. We're going to write it out. So if I take 2.71 and multiply it by -2, we get 2. 7 times 2 is 14. We get approximately -5.42. And we know that we have, just like we did in Skill 1, that horizontal asymptote that's going to get moved by your K value. So for this particular exponential function base E, we're going to say the horizontal asymptote is at y equals 3. So let's sketch that in. 3. Okay, and we have a point at -1, 1. 0, 1, 2, 3, 4, 5. Holy smokes, that's way down there. Man, what's this going to look like? Think back to the parent function. The parent function, if I were to dash it in, is going to look like this, right? Well, we have a vertical reflection, which means it's flipping upside down. It's reflecting across the horizontal asymptote. And then we have a vertical stretch. So to sketch this in, I'm simply going to start at the horizontal asymptote, and then I'm going to curve, and I'm going to curve quick so that I can include the 2 points representing a vertical reflection and a vertical stretch. So if ever you need to sketch in the parent function to sort of help you visualize what's happening, highly suggest that, because we're only dealing with 2 points here, and we really need to be comfortable with the shape and how our transformations are affecting that shape. Yay! Okay, so that is skill 3. My suggestion would be to not jump into skill 4 right away. Maybe set a timer for yourself for 10 to 15 minutes. Do a little bit of the homework, not all of it. Again, just set a timer for about 10 to 15 minutes so that you can play around with the skill and then watch the video notes for skill 4. Remember, both video notes need to be finished before class is over today. All right? All right. See you Friday. Oh, well, see you in about 15 minutes on our next video notes.